Welcome, everyone. This is our Math 60 video lecture. We're going to cover sections 6.1 and 6.2 today, which are all about ratios and rates. So a ratio is a fraction where the numerator, the top, and the denominator both have meaning. All right, they're not just numbers. It's not just a number 7/2 or whatever. It's the 7 has a meaning and the 2 has a meaning. So basically what we're doing is we're taking mathematical ideas and we're applying them to real situations. So one example that you've seen before is the idea of slope. The slope is the change in y divided by the change in x. So if we have a slope equal to 7/2, the numbers in the top and the bottom have meaning now. This means every time x goes right by 2, y goes up by 7. All right, the top and the bottom have some meaning. Other common ratios are things like 4 out of 5 dentists approve, if you've ever seen that. They approve this toothpaste, they approve this floss, whatever it may be. The ratio here is 4/5, where it's 4 are the dentists who approve, out of 5, and it's really every 5 dentists. Right? 4 dentists approve out of every 5 dentists. Notice I could have said 8 out of 10 dentists approve. Because 8 out of 10 would say 8 dentists approve out of every 10 dentists, and that fraction reduces to 4/5. So often ratios can be represented in reduced form, mostly in order to make the quantitative reasoning easier. All right, I could say 28 out of 35 dentists approve. But carrying those numbers in my head is a little more challenging. 28 out of 35 reduces to 4 out of 5. So it's easier to say 4 out of 5. The ratio is the same. And ratios can often be represented as percents. 80% of dentists approve. Well, percent in Spanish, por ciento, just means out of 100, right? So this really means 80 out of 100, 80 over 100, which again reduces to 4 out of 5. So not always, but very often ratios can be represented as percents, and any percent is actually a ratio. Any percent is a ratio out of 100. Okay. So in this section, there's sort of two questions we ask about ratios. The first question is, how do I build a ratio from numbers? So let's say I'm eating colorful goldfish, and there are 16 red goldfish. These are goldfish crackers, not actual goldfish. 12 yellow goldfish and 14 blue goldfish, because I think they make those in my box of colorful goldfish crackers. I can build ratios from these numbers. I can look at, for example, the ratio of red to yellow goldfish. When I say 2, I'm looking for division. The word 2 implies you're going to divide the first category by the second. So I'm going to be looking at the number of red divided by the number of yellow. Well, there are 16 red goldfish and 12 yellow goldfish. So this is the ratio of red to yellow. And often I would reduce that. 16 and 12 are both divisible by 4. 16 and 12, 16 divided by 12 is equivalent to 4 divided by 3. So this is the reduced ratio. For every 3 yellow goldfish, there are 4 red goldfish. Or for every 4 red goldfish, there are 3 yellow goldfish. A ratio contains 2 pieces of information. It is not, we no longer see it just as a single fraction. We see it as 2 pieces of information organized in this way with the division sign. I could also say, what's the ratio of blue goldfish to all the goldfish? Now I'm looking at the number of blue over the number of all colors of goldfish. There are 14 blue goldfish. In terms of all the goldfish, there's 16 plus 12 plus 14 for all the goldfish. So notice in this case, the number ratio of blue to all, that number for the blue also occurs in the bottom because blue goldfish are part of all the goldfish. And then I do a little arithmetic. Let's see, that's going to be 42. This is the ratio. There are 42 blue goldfish out of, there are 14 blue goldfish out of 42 goldfish total. There are 14 blue out of 42 total goldfish. And this one reduces. Both 14 and 42 are even. And also actually both 14 and 42 divide by 7. So let's practice reducing by hand. 14 over 42. Well, 14 is divisible by 2 and 42 is divisible by 2. So I can cancel those 2's. And 21 is 7 times 3. So I can cancel those 7's and I get 1 out of 3. 1 out of every 3 goldfish crackers is blue. Right? Same statement of the ratio. 14 blue out of 42 total is the same mathematical phrase as 1 out of every 3 goldfish is blue. Of course, if you only have 3 goldfish, that isn't much of a snack. So ratios often lose quantities. 1 out of every 3 goldfish is blue. Well, maybe that means I have 100 blue goldfish out of 300. Or maybe it means I have 2 blue goldfish out of 6 total. Right? It doesn't tell you how many goldfish I have. It doesn't even tell you how many blue goldfish I have. It only tells you the ratio. 1 out of every 3. As opposed to this statement here, there are 14 blue out of 42 total. That tells me the ratio and also the quantity. So reporting a reduced ratio can lose information. And maybe that information isn't that important. Maybe you just care what the ratio is. This came up when I was working as an epidemiologist, someone who works with public health data. But sometimes reporting a ratio, you kind of lose track of the fact. Like if you say 1 out of every 10,000 people has a certain medical condition, that seems like a very small fraction. But if you realize there are 100,000 people, that's 10 human beings who have that, and that matters. That's 10 people whose lives are affected. So reporting a ratio can lose information, and you as the person, the scientist, whatever, has to decide, do I want to report my total numbers or just my ratios? In this class, we're focusing more on how to report those ratios. Okay, so how do I build a ratio from numbers? That's one question that we might ask. Another question we might ask as a ratio is, how do I find numbers from ratios? All right, so basically working backwards. 3 out of 5 days are sunny in Bend. How many days of sun does Bend get in a year? Well, we know there are more than 5 days in a year. 3 out of 5 days is not telling us how many days there are total, right? So if I want to know how many days of sun does Bend get in a year, I know the ratio 3 out of 5 should be the same ratio as if I have 365 days. 3 out of 5 days equates to how many out of 365? And now I have a fraction equation which I solve for x. And the easiest way to solve this equation for x, and in fact, there are lots of different ways to do it, but the easiest is just to multiply both sides by the 365. Because that's going to cancel the x on both, or the 365 on the right, and end up with 365 times 3 over 5, which equals out to 219. Often we find numbers from percentages. 72% of, I just picked that number randomly and now I don't think of, let's see, 72% of cats are tabby cats. Sure. How many, let's see, if I have 50 cats, how many do I think will be tabby cats, like striped? Well, 72%, as I said earlier, is always a ratio 72 out of 100. And anytime we divide a number by 100, it's just taking that number and sticking it next to a decimal, right? 0.72 is equivalent to 72 out of 100, which is what 72% means. So I would just take 0.72 times 50, and I would get 36 tabby cats out of 50 total. Right? So we are finding numbers when we start with ratios. All right. The next idea from this section is finding unit rates from ratios. So one unit rate that we work with a lot is speed, miles per hour. That's how many miles you travel for every hour. Per here, it means for every. And it also indicates you're doing a division. Just like percent, divide by 100 per hour. So for example, I drive 120 miles in 3 hours. Maybe I stop, maybe I hit traffic. And I'm not saying I'm driving at a specific speed, but I could ask, what is my average speed in miles per hour? So I would take my 120 miles, divide it by my 3 hours, and this hopefully reinforces a ratio is not just a fraction, it is a numerator and a denominator that both mean something. 120 miles is a very real thing, and 3 hours is a very real thing. Now I can reduce that to 40 miles for 1 hour. And so I would say 40 miles per hour. Right? That's my unit rate. Every hour I travel 40 miles on average. Every hour I drive 40 miles on average. Maybe there was some highway driving, maybe there was some city driving, so I'm going faster and slower, but on average, my unit speed, my unit rate is 40 miles per hour. And another example we see often is unit price. So a 12-pound turkey costs, oh, I shouldn't use 12 because that's the same number. Let's do a 14-pound turkey. A 14-pound turkey costs $5. What is the price per pound? And having finished Thanksgiving week, I can tell you that this actually is a reasonable price for turkey. I was surprised when we went to buy our turkey. Right, the price per pound, that's a unit price. For every pound of turkey, how much do you pay? And so we build our ratio, 14 pounds divided by $5. Right? Again, that's a real numerator and a real denominator. They have actual meaning. Well, that's the rate, but it's hard to see as a fraction, right? So usually we're going to convert to decimals when we do rates. And so you just grab your calculator and you do 14 divided by 5, and we're going to see it's, did I do that right? Price per pound. I did that wrong. Can anyone see what I did wrong? Price per pound. So which should go on the top, the price or the pounds? Well, price, because it's price divided by pounds. Right, this means price divided by pounds. I could do the other ratio and look at the pounds per dollar, but that's not how we think about the cost of food. So it should be $5 divided by 14 pounds. And we're still going to convert to decimals. But now we do 5 divided by 14. And we get about 38 cents a pound. 0.38 dollars per pound. Which is exactly what we paid when we bought a turkey on Saturday. Because it was after Thanksgiving. We got it. It was great. Now we have 2 turkeys. So we can do, so these are called rates, but what it really is a unit rate, right? We have a ratio and we find not the miles for every 3 hours, but just simply the miles per every single hour. We don't find the cost of a 14-pound turkey, we find the price per pound of turkey. Okay. And then the last idea in this section comes from geometry. So if we take a circle and we draw a line right through the middle, that's called the diameter. And if we imagine taking a walk all the way around, the distance we walk is called the circumference. So the diameter is the length of a line through the center of the circle. And the circumference is the length of the walk around the circle. And no matter the diameter, whether it's 1 unit or 10 units or 39 units or 68.5 units, no matter the diameter, the circumference is pi times the diameter. So we can actually, and this is how the Greeks and probably other cultures did it, define the number pi, which is 2 little vertical lines with a line over the top. Define the number pi as the circumference divided by the diameter. So pi is a ratio, and it's about 3.14. But that number goes on forever, it never stops, it never repeats in any logical fashion. So the number pi pronounced like the dessert, but spelled, if we don't use the Greek letter, we just write pi. Pi is a ratio. It's the ratio of the circumference, I spelled that wrong, to the diameter. Let's do an example. There's a circle, its diameter is 4. That means the circumference, it's as simple as saying it's 4 times pi or 4 pi. That is a number, But the thing about numbers that aren't written as decimals, it's hard for humans to know about how big that is. Right? If you were to go on a walk around the circumference, it's hard for us to know about how long that walk's going to be. If I say, well, it's going to be 4 pi, you're going to be like, that doesn't help. So instead, we say it's about 4 times 3.14. And we grab our calculator. Most calculators have a button for pi, which is a more accurate decimal than 3.14. But it's about 12.56. So if you took this circle with a diameter 4 and you went on a walk all the way around it, you'd walk around about 12.56. And when the Greeks and probably other mathematical cultures discovered this number, they realized how important of a number it is. And it is actually super important. It shows up a lot of places where you might not expect beyond geometry. But we can look at more circle geometry. So another part of a circle we might care about is this distance from the center to any point on the circle. First of all, no matter, as long as you start in the center, that distance is always going to be the same, whether I walk that way or walk this way or walk that way, because it's the center. And the thing about a circle is it's the center is equidistant from every point on the circle. Okay, the distance from the center to any point on the circle is called the radius. And the ratio of the radius to the diameter is 1/2. But more often we say the diameter is 2 times the radius, or D equals 2R. Because if you have a circle, doesn't matter what size it is, and you take any radius, let's say that radius there, and then you extend it across to the other side of the circle, you've got a diameter. So 1 radius gets you halfway, so 2 radiuses get you a diameter. And this means that the circumference, which equals the diameter times pi, is 2 times the radius times pi, because the diameter is 2 times the radius. So, for example, a circle of radius equals 7 has a circumference of c equals 2 times 7 times pi, 14 pi. That's exactly the circumference, which is about 14 times 3.14, which is about 43.96. And the area of a circle, we can't use any rectangles or triangles to help us, but the area of the circle is pi times the radius squared, which is kind of an interesting idea. A equals pi r squared. So not only can we find the circumference of a circle with radius 7, we can find the area. It's pi times 7 squared, which is pi times 49. If we want our exact answer, we write 49 pi. And because that is hard for humans to see about how big that is, it's about 153.86 units squared. So the point I want to make is the number pi was developed as a ratio. Egyptians, I think, were actually the first folks to record that discovery. They just drew a whole bunch of circles and they started measuring across and they measured around and they realized no matter what circle I draw, if I take the distance across and I multiply it by 3.14, I get the distance around, right? And they realized, oh, that's a fixed ratio. That holds for every single circle. Okay, we are ready for section 6.2. 6.1 was mostly introducing what ratios were and working with them when they're mostly numbers. 6.2 is solving proportions, which is just another word for ratio equations. We did this actually already. We said 3 out of 5 days in Bend are sunny. How many sunny days in a year? And the way we did it is we built a ratio with the numbers we knew, and then we built a ratio with the number that we're looking for, where X is the number of sunny days in a year out of 365 days. And now we have a ratio equation We solve this ratio equation by solving for x. A lot of ratio equations boil down to a fairly simple one fraction equals x over another number. And so all we have to do is we take the 365 and we multiply both sides by 365 and we get x equals 219, which I did earlier. And that's the simplest ratio equation we might solve. And we could build more complicated ones with clever examples, but I'm just going to show you a couple purely numerical ones. So the simplest is when you have a fraction equals x over a number, because you just multiply by that denominator. You could have let me do different number. Let me do 35. You could have a ratio equals 35 over x. So maybe there are 7 grapes for every 2 apple slices on a fruit tray. If there are 35 grapes, how many apple slices are there? And so 7 over 2 equals 35 over x. Because I know the number of grapes, I'm looking for the number of apples. Well, we still need to solve, but x is trapped in a denominator. There are 2 ways to get x out of the denominator. One is using basic algebra, the other is using logic. So I'm going to demonstrate both. The basic algebra way says, if I don't want x in the denominator, I'm just going to multiply both sides by x. Because 35 times x divided by x, those x's cancel. And now I have 7 halves x equals 35, and I'm solving a fraction equation. So I say, what's the operation that I'm trying to undo? If I have 7 over 2x equals 35, what operation do I need to undo in this equation? That's the number. What's the operation? What's the operation that I'm trying to undo? This is a multiplication. So I would undo with division, right? Because that's what I want you to work on. Every time you have to solve an equation, your first step is to identify what operations do I have to undo. So this is a multiplication. So I'm going to undo it by dividing by 7 halves. Right? I'm going to divide by 7 halves on both sides. But divide by a fraction is the same as multiply by the reciprocal. So you still need to be working on your fraction skills because they still come up when you're doing other types of mathematics. So really, I want 7/2 x, and I'm going to multiply it by 2/7. Because that's going to cancel the 7/2, leaving me x on the right side, and then 35 times 2 all over 7, which is 70 over 7, which is 10. So there are 10 apple slices. Okay. Now, the other way to solve this, which is more of a logic step first than an algebra step, is to say, same question, 7 over 2 equals 35 over x. And if I think about this as ratios, 7 grapes to 2 apple slices. Is the same thing as 2 apple slices to 7 grapes. Would you agree? Yeah, there are 7 grapes for every 2 apple slices. Well, there are also 2 apple slices for every 7 grapes. So instead of writing it as 7 grapes over 2 apple slices, I can write it as 2 apple slices over 7 grapes. And that just means I'm looking for x apple slices over 35 grapes. So you flip both sides. If you flip both fractions, you're still equal. And now I'm back in my super easy example, right? Where I only have to solve that equation, which is as simple as multiplying both sides by the 35. Right? There are fewer steps involved. And I still have 70 over 7, which is 10, which is x. Because ratios, a ratio is just 2 pieces of information. And you can have either piece of information on the top, as long as you stay consistent. So this is often how I solve equations where the variable's in the denominator. Is the very first thing I do is I'm a mathematician. I don't like solving things where the variable's in the denominator. So I just rewrite it so the variable's in the top. And as long as I flip both sides, they're still equal. Okay. So here's a different example, but pretty similar in the end. Mm. Mm. There are multiple ways to solve this, but I'm just going to show you one and say, like, this is the way I want you to work on solving it. Okay. So let's look at x plus 5 over 18 should be the same ratio as 52 over 90. Now the difference is it's not x all by itself. But I can still use the same procedure. The issue is I'm dividing by 18. So I'm going to take the x plus 5 over 18, and I'm just going to multiply both sides by that 18. Because that x plus 5 is just sitting up there kind of in a parentheses. And so I get to cancel those 18s. And now I have freed the x plus 5 from the fraction. And I just do a little bit of multiplication over here. 18 times 52 over 90 is 10.4. Well, now I got to solve a one-step equation using or by undoing addition. All right, so I subtract 5 from both sides, and I have x equals 5.4. Okay. Let's do one more example, step up the difficulty a little bit more. This is going to involve a lot of different pieces, but as long as we track through it using our skills one at a time in the correct order, we'll be fine. I have 24 over 2x plus 2. And that ratio should equal 44 over 4x minus 3. Now, I'll be honest, I can't think of a physical situation that would give me these numbers. But it's a good chance to practice our skills. First, notice the variable is in the denominator. And I don't want it to be in the denominator. So what can I do? I'll just flip both sides because the ratios convey the same information regardless of which is on top. Now I have to flip both sides in order to make sure they're still equal. If I only flipped one side, they wouldn't be equal anymore. Now I've got them trapped in fractions, so I'm going to multiply by the denominators. So I'm going to do both sides times 44. I'll do it one step at a time. And let's add some redundant but helpful parentheses to keep track. And that's going to cancel the 44 on the right side. And before I do anything else, I'm also going to multiply both sides by 24. This is called clearing the denominators. Because that's going to cancel out the 24. And what I'm left with is now, it's a complicated equation, but at least there's no more division. Because division tends to be more complicated than multiplication. Now I go back to my other skills, which are distribute and collect like terms. So the 44 multiplies by the 2x and also by the 2. 44 times 2x is going to give me 88x. Am I keeping track of all my numbers? Yep, I haven't switched any by accident. 44 times 2 is 88. 24 times 4x is 96x. Calculators are fine. And then a minus 24 times 3 is minus 72. We're going to collect like terms. So let's get all of the x's onto one side. And I think it's a little easier if we subtract the 88x. So we end up with positive x's. 96 minus 88 is 8x. And then let's get this 72 to the other side. All right, we're back now to a simple multi-step solve a linear equation. 88 and 72 is 160. So 8x is 160. And the last step is divide both sides by 8. And we get 20 equals x. And we're done. Now to remember, to solve this initial equation, we're finding the x value that makes it true. And the x value that makes it true is 20. Lots of steps to do this. But the new piece was these two steps here, basically. The idea of I don't want my variables in the denominator, so I'll just flip both sides of the equation. And then to get rid of those two divisions, I'm going to clear the denominators. And now I'm back to distributing, collecting like terms, and solving. All right. Last idea from this section is similar objects in geometry. So we're back to geometry. Objects in geometry are similar if they have the same shape but not the same size. So for example, this rectangle, which is a 3 by 8, is similar to this other rectangle because they have the same shape, but they're not the same size. So if that's like a 1 right there, and I'm looking for the length, what is the length of the smaller rectangle? I can organize the information into a ratio. If I have 8 over 3 is the ratio of length to width of any rectangle of that shape, regardless of how big it is. If it has that shape, then the ratio of the length to the width must be 8 over 3. So that means 8 over 3 should have the same ratio as L over 1. And I multiply both sides by 1. And I get that L equals 8/3 or about 1.67. $2.67? I think it's 2.67. 2.67. Yeah. Let's do another example where we use triangles. Here's a triangle where that side is 10, that side is 12. And suppose I don't know that side X. And then I look at another triangle that's smaller, but is otherwise the same shape. That side here is 5. And I don't know that side Y. Let's find Y. And we're going to find Y by building a ratio using Y. So Y over 5, that's just organizing those two side lengths that I know. Y over 5 is saying one side is Y, the other side is 5. And that should have the same relationship as this bigger triangle here. And in the bigger triangle, what's the side that corresponds to Y? 10. And what's the side that corresponds to 5? 12. And now I can solve for Y. All right, so I organize my information because now the top and the bottom have real meaning. They're not just a single number, right? They're two different numbers that I organize together to have meaning. Solving for Y in this case as simple as multiplying both sides by 5. And I get Y equals 50 over 12. And working with geometry, I think it makes more sense to have decimals. 4.167 about. And now we do a quick check. 10 is a little bit less than 12. 4.167 is a little bit less than 5. Makes sense. I can also find X if I have more information. Like if I know that side right there is 3, that's going to tell me what X is. So now I can find X because I'll build, let's do X over 12 should be the same ratio as 3 over 5. If I take X over 12 equals 3 over 5, and I multiply both sides by 12, X should be 36 divided by 5. Let's get a decimal approximation, 7.2. And we do a quick check. 3 is the smallest length here. 7.2 is the smallest length there. Okay, that makes sense. All right, so the key is when you work with similar objects in geometry, you build ratios to organize your information. And once you have that information organized, you can usually solve for the missing piece. Okay, I'll stop recording now.